And welcome back. So we're going to continue looking at ionization energy, and in this presentation we're going to be focusing on first ionization energies. So what should you know by the end of this video? Well, we're going to recap definition for first ionization energy. We're going to be looking at the first ionization energy of different elements, and you should be able to predict patterns. And we're going to look at an actually past paper question and go through how to answer it. Okay, so questions looking at first ionization energy are often about comparing different elements. You should become familiar with graphs such as this. This shows the first ionization energy as you go from element to element, normally across a period. So before we start looking at what the actual questions are, we need to look through and be able to explain what is happening in this graph. So first bit, let's look at this. Now this is the first step going from neon to sodium. Now you can see there is a huge decrease in the first ionization energy between these two elements. Now in the previous video we looked at different factors which contribute to the magnitude of ionization energy. If you can't remember these, you may want to recap that video because we're going to be going into it in more depth in this example. So to explain this first stage, I'm going to once again draw the atoms in a GCSE manner, but hopefully that should be good enough to explain the theory behind the magnitude of the two values. So with neon, there are two full shells. You're going to be removing the electron from the outer shell, the second shell in this case. So you're going to be breaking this attraction here between the outermost electron and the nucleus, which in neon's case has 10 protons, hence the plus 10 I've put in this diagram. So that's the attractive force you have to overcome. You also have repulsion from the electrons in the first shell. So this has a certain value, as you can see from the graph, a little bit over 2000 kilojoules per mole. But then there's a huge drop to sodium. Why? So here you have the attractive force between the nucleus, which is plus 11 in this case, because there are 11 protons in the nucleus of sodium, and the outer electron. Now at this time, this electron is in the third shell. So that's the attractive force. And then the repulsive force comes from 2 shells worth of electrons. There are 10 shielding electrons in sodium in the first 2 shells. So why does the number decrease so much? Now you might be thinking, there's more protons, why isn't the number greater? Well, that is a factor, but the main factors here are the fact that the outer electron is now in the third shell, hence the atomic radius is much greater, and there are many more shielding electrons. So these two factors mean it is much easier to remove that outer electron, hence sodium has a much lower first ionization energy than neon. Okay, for this next stage, you can see there is a small increase between sodium and magnesium. Now, why is that the case? So with magnesium, the outer electron is still in the third shell, and we still have repulsion from 2 full shells worth of electrons. There are still 10 shielding electrons. So why are the values of first ionization energies different? Well, the key point here is the nuclear charge. Now for sodium, there are 11 protons in the nucleus, hence there's a nuclear charge of plus 11. For magnesium, there are 12 protons in the nucleus, so it has a charge of plus 12. Therefore, the nucleus is attracting the outer electrons more strongly in magnesium than sodium. So hence, the outer electron is actually slightly closer to the nucleus. The atomic radius is slightly smaller for magnesium than it is for sodium. So why does the ionization energy go up? There's a higher nuclear charge, a smaller atomic radius, the same amount of shielding electrons. Hence it is harder to remove that outer electron, hence having a slightly higher first ionization energy. Okay, next, going from magnesium to aluminium, you can see there is a drop in first ionization energy. So for magnesium, the outer electron is still in the third quantum shell. You still get repulsion from the first two shells. So you might be thinking, based on what we talked about going from sodium magnesium, that there would be an increase. Why is there a drop? It seems to be the same sort of pattern. Now, we can't explain this just using our simplified GCSE diagrams, so we are going to have to incorporate information we've already done so far in this course. So if I just fill in the orbital diagrams for magnesium, so we have 1s2, 2s2, 2p6, and 3s2. Now all of these electrons here are the shielding electrons, and they are repelling the electrons in that outer shell. I mean, they're repelling each other as well, but that isn't relevant for this video. So these electrons are repelling the outer electron, which is in the 3s subshell. And for aluminium, 1s2, 2s2, 2p6, 3s2, 3p1. Now because we've moved into the 3p subshell, now the 3s subshell is actually slightly lower in energy than the 3p, hence it is slightly closer to the nucleus. This means that we do actually get a little bit of shielding from these 3s electrons. So even though the nuclear charge has increased, this is compensated for by an increase in shielding. So from our simplified GCSE diagrams, you would have expected an increase in first ionization energy, but incorporating the extra knowledge you've gained this year, you'll hopefully be able to see why there is actually a decrease. So then afterwards, aluminium to silicon, there's an increase. This is for the same reasons we looked at between sodium and magnesium. There is an increased nuclear charge. There is the same amount of shielding. The atomic radius is slightly smaller. It's harder to remove that outer electron, hence a higher first ionization energy. The same explanation accounts for the increase between silicon and phosphorus. The increase from sulfur to chlorine and the increase from chlorine to argon can also be explained using the same points. So the one I've missed out is here. Now this is the last one I'm going to explain. Okay, so phosphorus, 1s2, 2s2, 2p6, 3s2, 3p3. Now hopefully you can remember when you are adding electrons into a p subshell, you must put one electron in each orbital, as I've done here, before you pair them up. Now with phosphorus, we now have an unpaired electron in each of the orbitals. So therefore, when we draw out the electronic configuration of sulfur, we are adding the last electron into an already occupied orbital. Now why is this significant? The electrons in this paired orbital are actually repelling each other. This has increased the amount of repulsion within the atom. Now because of this increased repulsion due to the outer electron being in a paired orbital, this actually makes it easier to remove that electron. Hence, the first ionization energy slightly decreases despite the increase in nuclear charge. So this accounts for this dip going from P3 to P4. Okay. So this is all the theory you need to be able to explain first ionization energies across a period. So let's have a look at the questions relating to this data in the past paper question. So part A, define the term first ionization energy. This is just what we did in the previous video. So the first ionization energy is the energy required to remove one electron from a mole of gaseous atoms of that element. So where do you get your marks for? Because there are actually 3 marks for this definition. So first mark is talking about the energy required per mole, is the first mark. Second mark is talking about removing one electron. And the third mark is mentioning that the atoms have to be in the gaseous state. So you get 3 marks for this definition. It's certainly worth remembering. Okay, the second question is also worth 3 marks. And it's asking about the general trend in the first ionization energy as you go across a period. So as you can see, the general trend is to increase. And this is to do with the factors we were discussing earlier. As you go across a period, the nuclear charge increases because the number of protons in the nucleus increases. This makes the attraction to the outer electron stronger. Hence, it is harder to remove. That would get you 1 mark. There are the same number of shells. This is relevant because it means the outer electron is in the same shell. So there is approximately the same amount of shielding. Now we talked about the first dip being caused by a slight increase in shielding from the free s electrons. This is only a small increase in the shielding, and generally is about the same amount of shielding. So the attractive force increases because of the nuclear charge increasing, but the repulsive force, the one acting in the opposite direction, remains about the same. Hence, overall, that outer electron is more attracted to the nucleus, hence a higher first ionization energy. This would be enough to get you all 3 marks. You could also make mention of the fact that because of these factors, the radius of the atoms generally decrease as you go across the period. So these are key points you need to include in answering this type of question. Next, explain why the first ionization energy decreases from phosphorus to sulfur. We've already talked about this. So in sulfur, the electrons in 3p subshell are paired for the first time, and this increases the amount of repulsion, hence making it slightly easier to remove that outer electron. So this would be how to get the 2 marks, and I've underlined key words in these sentences. You might want to phrase your answer slightly differently, but make sure you've included these 2 words. And last but not least, estimate the value of the first ionization energy of potassium. Write your answer below. So you can see here that potassium doesn't have a value for the first ionization energy because they want you to estimate it. So only 1 mark. Now, what do you have to consider? Potassium, the outer electron is in the next shell. Therefore, it is further from the nucleus. There is a whole extra shell of shielding from the 3rd shell. So the ionization energy is going to be much lower. Now you can't just put it lower. We've already discussed that as you go down a group, the first ionization energy decreases because of the increase in atomic radii the increase in shielding. So your value for potassium has to be below that of sodium. Sodium is in group 1, potassium is in group 1. Because potassium is further down the group, the first ionization energy must be lower. Now, they would have accepted any value between 200 and 490. The actual value is 419, okay? But you could have had any value between 200 and 490. You're not expected to know the exact value, but you should be able to use your knowledge to make predictions about the trend. So there you go. Hopefully we've reminded you the definition for the first ionization energy. You should be able to compare first ionization energies of different elements, especially going across a period. And hopefully you can now answer exam style questions on this topic. If you're still unclear about any of this, please review the video, and I'll see you in class.